Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving this hard problem where it states that you're given an n cross n binary grid. So n cross n matrix given to you consisting of ones and zeros. Now the task is you can change at most one cell in the grid from 0 to 1. Okay. You need to find the largest group of connected ones. So after changing 0 to 1s, you have to find the largest group of connected ones. Okay. Now remember one thing, two cells are said to be connected if both are adjacent to each other and both have same value. Let's quickly understand the problem with this particular example. So what they're saying is, if here's a 1, you can say them to be adjacent because they are sharing a common side. So if they share a side on the top, on the right, on the bottom, on the left, then you can call them as adjacent cells. Okay, so I can say this is a component in itself. Why? This is connected to this is connected to this is connected to this is connected to this, and this is connected to this. And you can say this, even if it is not, it's still a connected component of size 6. So, what are the other connected components in this particular n cross n matrix? If you carefully see this is also a connected component of size 6. Also, if you carefully see, we have another connected component of size 7. Now, point to notice, there is a connected component of size 6, 6, and a 7. But you cannot say this to be connected. As I clearly stated, no diagonals. Only top, right, bottom, and left is where you can connect someone. So over here, we have a size 6, we have a size 6, we have a size 7 connected components of ones. Now, you are asked to convert any 0 to 1. Imagine I convert this 0 to 1. Just imagine this is 1. Then can I say this is the new connected component with a size 6 plus 6, which it was previously, and a 1 as of now, which will make the total size to be 13. Okay. Can I convert this? Yes. You're allowed to convert anyone. If you convert this, it's still 6 plus 6 plus 1, which is 13. But, if you convert this, you actually connect all the three connected components, making it 6 plus 6 plus 7 plus 1, which is 20. And this is the largest that you can get. So you can try converting every 0 to a 1. And you need to tell me what is the largest connected component that you can get if you're allowed to convert a 0 to a 1, at most 1, not more than 1. Okay. So let's look at the second example. So we have 1, 1, 1, 1 here, which is of size 4. Again 1, 1, 1 here, a size 4. And another with a size 10. Now, if I convert this, I will have something like this, which will be of size 4 plus 4 plus 1, 9. If I try to convert this, I will still have the same size 9. But if I try to convert this might be connecting only one component, but it will still be a size 10 plus 1 equal to 11. 10 for the component itself, and you converted a 0 to a 1, so it is a 11 now. So the largest that you can get is 11. It's not necessary that you have to connect component to component. You can just convert a 0 to 1, and you see it is getting connected to the sidewise component. Make sense? So the answer for this will be 11. The answer for this will be 20. Okay. Now the question arises, how do we solve this problem? What are we looking at over here? We're looking at components. That's the first thing. Graph data structure. Whenever we see something as components, graph is the first thing that comes to my mind. What's the next thing? We're like, okay, convert this and the graph gets extended. Maybe convert this and the graph gets extended. Maybe convert this and the graph gets extended. What am I doing? I'm dynamically changing the graph. I'm dynamically changing the graph. And whenever the graph dynamically changes, which is the data structure? The data structure is disjoint set. Have I taught this? Yes. In the previous videos, I've taught this data structure. So please go back and watch that video because I've taught you everything about disjoint set data structure. At the end, I've written a code which can be reused in every problem of disjoint set, every problem, and we will reuse it over here as well. So go back and watch it just in case you haven't seen my video of disjointed data structure. Okay. So we know one thing. This is an n cross n matrix. And how does a disjointed data structure looks like? It has a node 0, it has a node 1, parents to himself, node 3, node n, and everyone is a parent to himself. But over here, what do we have? We have cells. We have cells. And if I consider this cell, this is 2 comma 3. So a cell is represented by two people, which is a row and column. So can I represent two people in a disjointed data structure? No. We know the data structure is basically a node with parent to himself, a node, a single number. So I need to somehow convert this n cross n matrix into cells of single number, because as of now, every cell is represented by a row and a column, which I do not want. So that's my first thought process. I need to somewhere convert the n cross n matrix into cell numbers so that I can map or use our disjointed data structure. So in order to convert an n cross n matrix into node numbers, can I say this? I have, oh my bad, I have 5 columns and 6 rows, which makes it a total of 30 cells. So I'll be like, okay, I have 30 cells. I'll represent every cell from number 0 to number 29 in zero based indexing. Now, how will I do this? Very simple. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. 27, 28, 29. But the point is, will I manually do this? No. What I'll do is, I'll go ahead and deduce a formula so that if I give you any row column, you can tell me the corresponding node number. Now I need to figure out the formula. Let's carefully observe something. First row is what? 0, 1, 2, 3, 4. Can I say 5 people went to the first row? Yes. And this starts from 0. This starts from 5, 6, 7, 8, 9. Can I say 10 people went in the first 2 rows? That's why 10, 11, 12, 13, 14. Can I say in the first 3 rows, 15 people went? That's why 15. So if you carefully see a pattern, since 5 people are going, it's in the multiple of 5. It starts with a multiple of 5. It starts with a multiple of 5 because 5 are going, 5 are going, 5 are going, 5 are going. So it's very obvious that if you start with 0, you're going to end with 4. And this will be 5. This will be 9. This will be 10. This will be 14. This will be 15. This will be 19 and so on. So can I say, if I'm looking for this row and this guy, can I say this? I know what is this guy. 4 into 5. Because previously there were 4 rows. So 4 into 5, 20 people have gone. So this will start from 20. And if I'm looking for this, can I say this much is what I have to travel, which is 2. So can I say, if I'm looking for this, I can say 4 into 5 because I've traveled 4 rows and everyone was 5. So 4 into 5 and I have to travel this much. So that's 2, which makes it 22. So the cell number is 22. Got it. So the formula is very simple. Row into number of columns because those many have traveled plus the column, so that you just take the length. Like it is 20, 21 and 22. So you take the length 2 according to the column. So I figured out a formula in order to reduce the cell numbers for a given row and a column. Now, what is the next step? How should I think? Now, I'm like, what will I do? I've been asked to convert zeros to 1. So logically, I will do something like this, like the brute force, the extreme naive way will be. I'll convert this to 1 and I'll look at the left if there is a connected component. And I'll look at the right if there is a connected component. And I'll look at the bottom, I don't find one. I look at the top, I don't find one. So on the left, I found a connected component of size 6. On the right I found a connected component of size 6 and a +1 for myself. So I'll get a total elongated connected component of size 30. Similarly, I can again go and convert this to 1. And again, I'll connect this 6. Again, I'll connect this 6. But wait. Now my mind is thinking, but if I'm converting this to 1, how am I knowing that this is of size 6? How am I knowing that this is of size 6? Okay. This is where my algorithmic skill says, hey, we can keep them as connected. And the data structure that does this is disjoints a data structure. So what I will do is I'll go and implement the disjoint set data structure and keep them as connected. Now, if you remember, this is 0, 1, this is 5, 6, this is 10, 11. So if you draw the disjoint set data structure, it will be like 0 and 1 will be connected, 5 will be connected, 6 will be connected, 10 will be connected, 11 will be connected with 0 being the parent. And how do you connect them? Very simple. You start with this one. So you take this one, which is the 0th cell, and you say, okay, look at the top, no one. Look at the right, there is someone. If there is someone, just take that cell number and connect it. So disjoint set will connect. Look at the bottom, and if there is someone, go and connect. Look at the left, there is no one. So in this way, you can connect at first this one with this 2B. Next, when you go to this one, you'll see no one, no one, and you'll connect with this one, right? Eventually, this guy was connected to this guy got connected to this. And when you come to this one, this will get connected to this. And when you come to this one, this will get connected to this. So in this way, for every one, you connect 4 directions using the disjoint set. So I'm not going into the depth because I'm assuming you know how disjoint set data structure works. So once I've made them connected, the disjoint set data structure will look something like this. Like these guys will be connected like this. These guys will be connected like this. I've converted them to node numbers and made them connected. And these guys will be connected like this. And if you're using union by size, at 0th position, you will have in the size array of 0 as 6. Over here, the size array of 3 will be containing 6. Over here, the size of 17 will be contained as 7. If you're using union by size in the disjoint set data structure, again, back to the previous lecture. I've already taught you that. Okay, pretty much understood. This is how the disjoint set looks like. Now, the point comes where we solve the problem, which is the step 2. Try converting every 0. That's it. To 1. So I go and try to convert. Do not convert. Just stand here because it's a 0. Look at the right. Okay. At the right, you figure out this cell, and this cell is 3. So you see 3 is the parent of himself. So you figure out the size of 3 is 6. So you add 6 to the answer. Now you look at here, and this is 1. And 1's ultimate parent is 0. So you figure out the size of 0 to be 6. So you know in total, you only have someone on the right and someone on the left. No one on the bottom because it's a 0. 6 plus 6 and 1 for itself. So you got a 13 size. Perfect. Next you again go here. And you look on the top, no. On the right, yes. We have someone. And what is his value? 8. So we see 8 is here. And the ultimate parent is 3. So you again find size of 3, which is 6. Similarly, if you find this, again you'll find 6 plus 1 and you get 13. Now, if you try to convert this, what will happen? So there is a 0. No one on the top. Over here, you get a size 6. On this, you get a size 7. On this, you get a size 6 and 1 for himself. So a total of 20. Similarly, you can go on converting every 0. And ultimately, you'll see 20 is the maximum that you will get. Wait. There is still an edge case. You have to think of an edge case before moving on. Do you only connect something on the top, right, bottom, left? If you do this, it will go as wrong. Let me show you an classical example. Imagine we are standing somewhere here. Okay. Imagine we are standing somewhere here. Now this guy looks at the top and gets a size 6. Very obvious, gets a size 6. This guy looks at right, gets nothing. This guy looks at bottom and gets a size 7. Correct? So basically from this it got 6. So 6, 7 and it got 0 from here. Now, when it looks on the left, it again gets the same 7 and 1 for himself, which is 7 plus 7, 14 plus 6, 21, which is actually a wrong answer. Why did this happen? Because this guy on the bottom got a 7 and this 7 was this component. This guy on the left got the same 7. So 7 was computed twice. What you should have done is, this one is nothing but, if I compute the value 20, 21, 22, 23 cell number. You see 23 cell number is pointing to parent 17. So what you do is, instead of storing the sizes Yes, instead of storing the sizes, probably you can take a set data structure and you can say, okay, now let's do again. Top, what's this? Let's have the cell number 10, 11, 12, 13 is the cell number. Where's 13? Here's 13. 13's ultimate parent, 3. Let's put parent as 3. So you got the parent as 3. We got the parent as 3 for this. Do not take the size as of now. Let's look at the bottom. What is this? This is 20, 21, 22, 23. Where's 23? Here. Who's the parent? 17. So let's pick up 17. On the bottom, we have 17. This was not valid. Again, let's look at over here. What is it? 15, 16, 17. So this is 17 itself. So 17's parent is 17. So if you put it into the set, it will not accept it because it's a duplicate. It's a duplicate component. So ultimately, once you have gone through all the directions, the set only stores 3 and 17. So you ask size of 3 and this will give you as 6. You ask size of 17 and you will get it as 7. Now summarize this as 13 and 1 for itself to make it 14. So you get the correct answer. So instead of just blindly taking the top right, make sure you put them into the set because there might be some component which is on multiple directions. It may be on the left and the bottom. It may be on 3 directions. It might be in the 4 directions. You might have a case where you have something like 1, 1, 1, 1, 1, 1, 1, 1. And in this case, there's a 0 here. So in this case, everyone is the same component. That's why take a set data structure, just store the ultimate parents and just take one component once. This is how I can make sure that this edge case is not missed. So I hope you have understood the entire explanation. Now it's time to code it up. So as usual, you'll find the C++ solution on the right and you can find out the exact similar Java code on the left. So we need the disjoints and data structure. I'll go and copy paste the snippet that I have been using. Whether I've explained the snippet in the disjoints video, just in case you haven't seen it, go back and watch it. So we know it's an n cross n grid. So the row and columns will be n itself. So done. Next, yeah, disjoint set. Size, the number of cells, which is n cross n. What's the next thing? Go across to all the rows. Basically traverse in the grid. So let's go across and traverse in the grid. So perfect. Traveling in the grid. Now I know one thing. I am over here to connect the components. And if it is 0, there is no need to connect the components. Perfect. Now I need to go, like if I'm standing somewhere, I need to go top, right, bottom, left. So all directions I have to go and connect them, connect. This is a 1. It has to be connected to 4 directions, right? So you know how to go to 4 directions. I am no more going to teach this. Come on. I've already taught you this in so many videos. In this particular series. This is why I'm asking you to watch this series. Because I've already taught you this. Okay. Now, what will I do? I'll go across to all directions. So index equal to 0, index lesser than 4, index plus plus. I'll be like, okay, new row is equal to the current row plus dr of index. And new column is equal to current column plus dc of index. Now, we got the top or the right or the bottom or the left. Once we have got the adjacent node, what do we need to check? Yes, is it valid? So go across and say, hey, is this new column valid against n? If it is valid, are they having a 1? Very, very important. They should have a 1. If they're having a 1, this one, or this one, or this one, connect them. ds dot union, maybe you can just copy paste this by size. But wait, you're connecting 2 people. So you need this cell number and this cell number. So 1 is the cell number of the node, which is the node number. Can I say it will be row into n plus column because n is the number of columns. And can I see the adjacent node number will be nothing but new row into n plus new column. Was it that tough? No. Now what you say is go across and connect the node number and the adjacent node number. Perfect. Now I just need to write this is valid function. So go across and make sure you declare it private because we are using it just for our use. So no need to declare it to the outside world. New column and IDN. So you can be like return if new row is this. At the same time, new row is this. At the same time, the new column is this. At the same time, the new column is this. If it lies inside the grids, it's a valid one. Let's go and check. So this is how you can connect everyone. So step one is done, which is connecting components. What was step two? Step two was to do the what is step two? It's very simple. Just do the simple brute force. So go across and do the simple brute force where you take every zero and try to convert it to a one. Do not convert, just try to convert. Okay. So over here, I can say it's going to be if it is a one, or rather over here also it will be row column rather, not ij, my bad. So over here, I can say if the row and the column is equal to something like 1, we cannot convert it, so go back. But if it is 0, I can. So I'll again follow the same tactic. Yes, I'll just copy paste maybe so that I don't have to rewrite. I'll follow the same tactic of dr dx, but this time we have a new r and a new c, which is the adjacent guy, right? So I will go across and say, firstly, is this a valid guy? So I'll call the is valid and again say, is this a valid guy? So what I did was, I am standing at a 0. I'm standing at a 0 of grid row column. I went to the top and I said, are you a valid guy? He says, yes, I'm a valid guy. Now, my task is very simple. If it's a valid guy, it has to be a 1, right? Because if it is not a 1, it will never be a component. So I'll be like, okay, are you 1? He's like, I'm 1 as well. Now I'm like, okay, you are 1. That means I can connect. I can connect with you. So if I can connect with you, you are someone, you are a component. So let's store the components. So maybe I can say set int compose a components. Let's store the components. So can I say components will be very simple of insert, but wait, will I store the adjacent guy or its ultimate parent? Obviously it's ultimate parent. So I'll be like, find u pair of this new r into n plus new column. So you go across and say, for this cell number, get me the ultimate parent and the components. So once you have traversed for all the 4 directions, you get all the components that you can connect to, right? And now you can figure out the size. Let's figure out the size. So can I say, I can just go ahead on the set, which is components, and I can say, hey, listen, size plus equal to, maybe what you can do is size total. Okay, that'll be better naming. Size total plus ds dot. So just make sure you expose these guys to the outside world as well, so that you can use the size. Okay, cool. ds dot size of it. Once you have got the size total, you need the max. Maybe you can store the mx as 1 or 0, whatever you wish to. And at the end of the day, you can say mx equal to max plus mx dot size total. Done. So this is how the step 2 will look like. So it's very simple. I just moved across to all the 4 directions, got all the components that it connects to, and just went across all the components, got its size and got it total. Now, so can I say that this will be accepted? The answer to that is no. Why? Now this is like converting zeros to 1. What if the cell has all ones? Okay, point to think. So we need to find the ultimate parent, right? Like you might have all ones, but we need to find the ultimate parent. So what I'll do is, I'll just for safety reasons go ahead and say, hey, listen, you just need to go to all the cell numbers. So it's from 0 to cell numbers n into n. And for all the cell numbers, just get the ultimate parent and update the max. So max of mx, comma, ds dot size, comma, ds dot find ultimate parent of what? The cell number. Whoever is the ultimate parent, get it and gets its size. Once you've done this, you can go ahead and return the mx. So before submitting this, a quick typo that I have done. You have added all the components, but the 0 that you converted to 1, you did not. So do a +1. Now let's quickly compile and see if it's compiling or not. Hopefully it does at one go. Oh wow, it does. Okay, let's submit. If this runs at one go, I will be satisfied. I am satisfied. such a huge code and at once is something which I absolutely love. So, guys, I hope you've understood it. Let's understand the time complexity. N into n into r, and the disjoint set is kind of constant. So, n square into r, n square into r. Set is using log n, but it's just four at max components. So, it's very minor because at max there will be four ultimate parents. So, it's negligible. So I can say n square is like near about the time complexity that we are using, and the space is over here, which is pretty simple to compute. So, guys, I hope I was able to explain you this problem. So, just in case I was, please do consider subscribing to us because I was going through our statistics and nearly 50% of the viewers who watch our video do not hit that subscribe button. So please do consider subscribing to us. And if you have watched the video till here, do consider hitting that like button as well so that I understand that you guys are liking these kind of videos. And also, if you haven't checked out our DP series and the SD sheet, the links will be in the description. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye bye. Take care.
Whenever your heart is broken.